Here is a question that I'd like you to ponder over as we go through the contents of this video. What kind of neural network has become really popular for image processing? Think different types of neural networks such as convolutional, recurrent, bidirectional, and so on. Let's now change tracks a little bit and switch from regression to working with images. We are not done with regression, not by a long way. We will get back to linear and logistic regression in TensorFlow in a great deal of detail. But before that, let's just talk about working with images because this is a fairly typical use case of TensorFlow in the real world. Regression is pretty much a solved problem. Even Microsoft Excel has a really powerful functionality on regression and has had this for the past few decades. Working with images, on the other hand, is something which is really new to the world of machine learning, and this is why TensorFlow is so hot. Working with hard to represent data like images and videos, this is where neural networks and deep learning really come into their own. Indeed, image recognition is really the starter problem in TensorFlow, as we are going to explore in just a moment. Working with images requires us to understand some basic operations. We need to know how to represent images in the form of tensors. And these tensors need to encode color as well as grayscale information. We will also learn some basics of image operations such as cropping, transposing, and resizing images. All of these will come in handy once we actually start using TensorFlow for more advanced stuff. So again, the basic idea is image recognition. The basic idea is to detect what an image represents from the pixels that constitute it. In case you're not familiar with the idea of pixels, every little region of an image can be decomposed into specific rectangular shapes called pixels. Pixels contain within them a wealth of information. They are a form of encoding. Let's understand how pixels can help with image recognition. In fact, pixels really are the features in our feature vector during the image recognition machine learning problem solution. We had hinted at this while discussing the use of TensorFlow for image recognition. There, we had spoken about how images are represented as pixels. Those pixels have higher level features such as edges, colors, and shapes. And on the basis of all of these, the basic building blocks, including the pixels, the more intermediate building blocks, the colors, shapes, and tints, we are able to recognize what that image represents. This is a process which the human brain is really good at. We take in an image at a glance. In fact, the human brain is able to encode information with images far more efficiently than using text. The efficiency of that encoding is exactly what gives rise to statements or proverbs like a picture is worth 1,000 words. Automating this, allowing machines or computers to do this, is what image recognition and machine learning are all about. We want a computer program which will take in the pixels, identify the higher level features, and ultimately tell us what that picture represents. Neural networks, specifically convolutional neural networks, are really useful. They are really popular for image recognition problems. And because neural networks are best implemented in TensorFlow, this is the tool of choice these days, image recognition has pretty much become a bread and butter use case for TensorFlow. Or to put it differently, TensorFlow is becoming the dominant tool, the technology of choice for folks working with image recognition. Let's understand this in just a little more detail. Let's see how image recognition can be achieved using neural networks at a high level. Here, the problem that we are going to set out to solve is a classification one. We have a corpus of images. We then have a feature selection and classification algorithm. This is going to rely on neural networks inside. We will pass the images in our corpus into this algorithm one by one. At the initial level, we will have a layer which deals with the pixels. Then intermediate layers within the neural network will deal with higher level constructs such as the edges, the contours, and so on. And then at the end of it all will come a final output layer, a classification layer, which will hopefully have the ability to classify the corpus of input images based on their content. So, for instance, maybe we would like to classify these images as belonging to either fish or mammals. This is something which the final step of the neural network would do. And that would imply that the output as a whole would be a trained classifier. This machine learning based classifier, after training, could then be passed in a new image and it would tell us whether that represented the image of a fish or of a mammal. It's important to keep in mind that this is a two-step process. So if you were surprised that the output of this neural network was not a label, but rather that it was a classifier, understand that the way machine learning and neural network algorithms work, you first train a model. You use the training data, the corpus of images, to tweak or optimize the values of the variables, the parameters in that model. And at the end of that process, you get a model which you can then use to actually classify new images. We had discussed that these layers in the neural network are called either visible or hidden, based on whether we, as the end user, actually understand what they are operating on. This is a quick introduction to neural networks. Do keep in mind how these layers in general are opaque to the programmer. And a big part of the challenge in designing good machine learning algorithms using neural networks is to wire up those individual neurons which are present inside these different layers, even though the working of those layers is more or less opaque to you, it's more or less unknown. As an example, you might have a neural network with a very dense set of interconnections. You might then go ahead and find that this dense set of interconnections causes your neural network to work well with your training data, but to fare poorly when given new data. You then will specify something known as a dropout factor. You will break completely arbitrarily at random a bunch of the interconnections in your network. This almost represents an act of faith because you have no idea whether this is going to help or hurt with the test data. This is something that you've just got to do because the science and the technology has shown that it works. TensorFlow is optimized, it's aimed at building neural networks like this one. Image recognition or text processing or any of these use cases using neural networks, all of these are preferred dominant use cases of TensorFlow. But do be aware that while you are using TensorFlow, you are going to have to accept that there is a lot going on under the hood within that network which you will not understand. Let's return now to the question we posed at the start of this video. Convolutional neural networks have become most popular for image processing. In fact, there is an algorithm called Inception which makes use of convolutional neural networks and has currently defined the best performance out there for image classification tasks. Other types of neural networks have their own specific use cases. For instance, recurrent neural networks tend to be used heavily in text processing for applications such as autocomplete or generating sequences of text which are similar to those written by an author. In cases where we have sequences of data kind of arranged in time, such as time series data, recurrent neural networks are more popular. Where we have spatially arranged data, such as pixels in an image, convolutional neural networks currently are the tool of choice.